Okay, so a definition: an operator T is said to be sublinear, okay, if absolute value of T of F plus G is less than or equal than absolute value of T of F plus absolute value of T of G. Okay, we will also say that T is a linear or sublinear operator of type PQ, okay, with a constant MPQ, if norm of T of F Q is less than or equal than MPQ norm of FQ for any F in all P. Okay, so we could rephrase the statement of the Ritz-Theorem saying that T is an operator, a linear operator of type P0, Q0, and T was also a linear operator of type P1, Q1, and both they were bounded by a constant. In this case was m0, and in this case was m1. So then we will say that the Ritz-Theorem theorem told us that the T will be a linear operator of type P theta Q theta. Okay. Okay, so an application of this can be the theorem of Hausdorff and Young's inequality. Okay, so let F in LP of Rn, okay, and P is between 1 and 2. Then F transform is in LP prime of Rn with 1 over P plus 1 over P prime is equal to 1, and the norm of F transform P prime will less than equal than the norm of F of P. Okay, so to show this, recall that the Fourier transform is of type well, type 1 infinity. It goes from L1 to infinity and L2 to L2, and in both cases it's with norm 1. Okay, so Ritz-Theorem tells us that it should also be a PQ operator, and this will be 1 over P equals to 1 minus theta over 1 plus theta over 2 equals 1 minus theta over 2, and 1 over Q will be, okay, so 1 minus theta over infinity is 0, and theta over 2, and this will be 1 minus 1 P, okay, because, well, you can tell it from just passing this the other way, and so, okay, this will be equal to 1 over P prime. Okay, and so recall what Ritz-Theorem told us about the bound that M was less than equal than 1 well, in this case will be 1 to the 1 minus theta, 1 to the theta, and this is equal to 1. So we obtain the bound that we were looking for the Fourier transform. Okay, so a definition for a measurable function f goes from x to the complex numbers. We define the distribution function as, okay, m lambda f equals to the measure of the set of the x, let's say x in big X, such that the absolute value of f of x is greater than the lambda, and we will call this the measure of e lambda f. Okay, so this m is a function of lambda that goes from 0 to infinity, and it takes values in 0 and infinity too. So one can see, let's say we have any function and then we have a lambda. Okay, so then we will have to know the measure of the x, let's say the set where f, the absolute value of f, is greater than lambda. So the values will be between 0 and infinity, and it's non-increasing because we, as lambda, as you increase lambda, then there will be less parts of the function uh, in the upper part of the graph. So it will be non-increasing. Okay, so some properties of distribution functions. So the first one is the Chebyshev. Okay, and it is that m of lambda f is less than equal than lambda to the minus p integral in e lambda f of absolute value of f of x p d mu of x, and this will be less than equal than lambda minus p, the norm of f p to the p. Okay. Another property, if p is between 1 and less than infinity, then we will have the norm of f p will equal to minus the integral between 0 and infinity lambda p and d m, okay, lambda f, and this will be equal to p multiplied by the integral from 0 to infinity of lambda p minus 1 m lambda f, and now it will be d lambda. In the case that p is equal to infinity, we will have that the norm of f infinity will be the infimum of the set of lambdas, so that m of lambda f will be equal to 0. So this last property is telling us about the normal infinity of f will be the infimum of the lambdas that we need, so that the function that we define, the distribution function, is equal to 0. That means that as lambda increases, there will be the first lambda where the function will not be in the set. That means that m will be equal to 0. And a third property, m of lambda f plus g is less than or equal than m of lambda over 2 f plus m of lambda over 2 j. Okay, so a definition for p between 1 and infinity, okay, this is less than infinity, we denote LP star, okay, of x, the space of all measurable functions f x to complex numbers, okay, measurable, such that norm f p star is equal to the supremum lambda m lambda f, okay, 1 over p, this is for lambda positive, and this must be less than infinity. Okay, so some properties of LP star. So first of all, observe that L infinity star is equal to L infinity, and you can also say that LP Rn uh, is included in LP star Rn, okay, with an L. And another property, the norm f plus g p star is less than equal to 2 multiplied by f p star plus g p star. Okay, so because of this, LP star x is a quasi-normed vector space. Okay, so a definition, let mx be the space of complex valued measurable functions, and defined on x, and so a linear or sublinear operator t that goes from lpx to mx with p between 1 and infinity is said to be of weak type pq. Recall that we already stated the strong type if there exists a constant c such that for any f in LP x, we have that norm t of f q star is less than equal than c norm of f p. So if q is equal to infinity, then weak and strong are agree. And because of Chebyshev's inequality, we know that this t is of type pq strong, then t is of pq weak. Okay,